Imagine a place so vast, so mysterious, that it defies everything we think we know about the universe. A place where galaxies dance in the dark, where invisible forces pull at the fabric of reality, and where secrets lie hidden in the depths of space. This is the Virgo Supercluster, a cosmic neighborhood that holds some of the most baffling and unexplained phenomena ever discovered. From galaxies that seem to defy the laws of physics to gravitational anomalies that tug at the very essence of existence, the Virgo Supercluster is a treasure trove of cosmic mysteries. In this video, we'll explore 25 of these mind-bending phenomena, each one challenging our understanding of the universe and leaving us with more questions than answers. So, buckle up and prepare to journey into the unknown where the mysteries of the cosmos await. Stay with us because by the end of this video, you'll see the universe in a whole new light. Now, let's dive into our first mystery, a discovery that has left scientists scratching their heads. Meet NGC 1052 DF2, a galaxy that seems to break one of the most fundamental rules of the cosmos. Unlike most galaxies, which are thought to be held together by the gravitational pull of dark matter, this one appears to have almost none. Dark matter, that invisible substance making up about 85% of the universe's mass, is supposed to be the backbone of galaxies. But NGC 1052 DF2 defies this expectation entirely. When astronomers first observed this galaxy, they expected to find the usual signs of dark matter, its gravitational influence on stars and gas. Instead, they found something startling. The stars in this galaxy move in ways that suggest there's almost no dark matter at all. This discovery sent shockwaves through the scientific community, challenging our understanding of how galaxies form and evolve. If dark matter isn't necessary for a galaxy to exist, what does that mean for our current theories? The implications are profound. For decades, dark matter has been a cornerstone of astrophysics, explaining everything from the rotation of galaxies to the large-scale structure of the universe. But NGC 1052 DF2 raises questions that are hard to ignore. Could there be other galaxies like this? Are we missing something fundamental about how dark matter works? Or is this galaxy an outlier, a cosmic oddity that doesn't fit the mold? Scientists are still debating these questions, and the mystery of NGC 1052 DF2 remains unsolved. Some suggest that it might have lost its dark matter through interactions with other galaxies, while others propose entirely new models of galaxy formation. Whatever the answer, this galaxy reminds us that the universe is full of surprises, and sometimes the rules we think we know are just waiting to be rewritten. As we move forward, keep this galaxy in mind. It's a reminder that even in the vastness of the Virgo Supercluster, there are still mysteries that challenge our understanding of the cosmos. And with that, let's turn our attention to the next phenomenon, another cosmic puzzle that defies explanation. Now, let's shift our gaze to another cosmic enigma that has puzzled astronomers for decades, the Great Attractor. Imagine a force so powerful that it's pulling entire galaxies, including our own Milky Way, toward it at incredible speeds. This mysterious gravitational anomaly lies hidden within the Virgo Supercluster, and despite its immense influence, it remains one of the most elusive phenomena in the universe. The Great Attractor is located in the direction of the constellation Centaurus, roughly 250 million light-years away. But here's the catch: it's obscured by what astronomers call the zone of avoidance, a region of the sky hidden behind the dense dust and stars of the Milky Way's galactic plane. This makes it incredibly difficult to observe directly, as our own galaxy's material blocks our view. So, what exactly is pulling us toward this unseen force? The answer lies in the distribution of mass in the universe. The Great Attractor is thought to be a massive concentration of matter, likely a combination of galaxies, dark matter, and other cosmic structures, creating a gravitational pull so strong that it influences the motion of galaxies across vast distances. But the exact nature of this concentration remains a mystery. Studying the Great Attractor is like trying to solve a puzzle with half the pieces missing. Astronomers rely on indirect methods, such as observing the motion of galaxies and mapping the cosmic microwave background to infer its properties. These observations suggest that the Great Attractor is part of an even larger structure known as the Laniakea Supercluster, a vast network of galaxies spanning over 500 million light-years. The challenges of studying this phenomenon highlight the limits of our current technology and the complexity of the universe. Yet, the Great Attractor continues to captivate scientists and stargazers alike, reminding us that even in our own cosmic neighborhood, there are forces at work that we are only beginning to understand. As we ponder the mysteries of the Great Attractor, let's turn our attention to the next phenomenon, another cosmic puzzle that challenges our understanding of the universe's structure and evolution. Now, let's dive into another cosmic mystery that has left scientists scratching their heads: the puzzling case of the Virgo cluster's missing baryons. Baryons, for those unfamiliar, are the building blocks of normal matter, things like protons and neutrons that make up stars, planets, and even us. Yet, in the Virgo cluster, one of the most massive galaxy clusters in the universe, a significant portion of these baryons seems to have vanished without a trace. The Virgo cluster is home to thousands of galaxies, each teeming with stars, gas, and dust. Given its sheer size, you'd expect it to contain an enormous amount of baryonic matter. However, when astronomers tally up the visible matter, stars, gas, and dust, they find that it accounts for only a fraction of what should be there based on our current understanding of the universe. This discrepancy is known as the missing baryon problem, and it's a mystery that challenges the very foundations of cosmology. So, where could these baryons be hiding? One leading theory suggests that they might exist in the form of hot, diffuse gas spread throughout the cluster, too faint to detect with current instruments. This gas, often referred to as the warm-hot intergalactic medium, could be hiding in the vast spaces between galaxies, invisible to traditional telescopes. Another possibility is that the missing baryons are tied up in dark matter halos or have been ejected from the cluster entirely due to violent cosmic events like galaxy collisions. The implications of this missing matter are profound. If baryons are indeed scattered in ways we can't yet observe, it means our understanding of how matter is distributed in the universe is incomplete. This challenges not only our models of galaxy clusters, but also our broader theories about the evolution of the cosmos. Efforts to solve this mystery are ongoing, with astronomers using advanced telescopes and simulations to search for these elusive baryons. Each new observation brings us closer to unraveling the secrets of the Virgo cluster, but for now, the missing baryons remain one of the most intriguing puzzles in modern astrophysics. As we continue our journey through the Virgo Supercluster, let's turn our attention to another phenomenon that defies expectations: ultra-diffuse galaxies. These faint, ghostly structures are as mysterious as they are fascinating, and they hold clues to the universe's most enduring secrets. Now, shifting our gaze to another cosmic enigma, we encounter the ultra-diffuse galaxies, faint, ghostly structures that challenge everything we thought we knew about galaxies. Unlike the bright, densely packed galaxies we're familiar with, these mysterious objects are incredibly dim and spread out, often resembling faint smudges in the vastness of space. Ultra-diffuse galaxies are so faint that they were only discovered relatively recently, thanks to advancements in telescope technology. Despite their low brightness, they can be as large as the Milky Way, but with far fewer stars. This makes them some of the most puzzling objects in the universe. Why are they so faint, and how did they form in the first place? One of the most intriguing aspects of ultra-diffuse galaxies is their prevalence in the Virgo Supercluster. While they can be found elsewhere in the universe, they seem to be particularly abundant here. This has led scientists to wonder if the unique environment of the Virgo Supercluster plays a role in their formation. Some theories suggest that these galaxies might be the remnants of larger galaxies that were stripped of their stars and gassed through interactions with other galaxies or the cluster's gravitational forces. Others propose that they could be ancient galaxies that never fully developed, remaining in a primordial state for billions of years. What makes these galaxies even more fascinating is their surprising amount of dark matter. Despite their lack of visible stars, many ultra-diffuse galaxies appear to be dominated by dark matter, which could explain their ability to hold together despite their low density. This discovery has opened up new questions about the relationship between dark matter and galaxy formation, challenging our understanding of how galaxies evolve. The study of ultra-diffuse galaxies is still in its early stages, but each new observation brings us closer to unraveling their secrets. Are they failed galaxies, cosmic relics, or something entirely different? As we continue to explore the Virgo Supercluster, these ghostly galaxies remind us that the universe is full of surprises waiting to be uncovered. Next, we'll turn our attention to another mystery that's shaking the foundations of cosmology, the Hubble Tension. This discrepancy in the universe's expansion rate has sparked intense debate among scientists, and its implications could change everything we know about the cosmos. Now, let's dive into a mystery that's causing quite a stir in the world of cosmology, the Hubble Tension. This puzzling discrepancy revolves around how fast the universe is expanding, and it's throwing a wrench into our understanding of the cosmos. At the heart of this tension are two different methods scientists use to measure the universe's expansion rate, and they just don't seem to agree. One method involves looking at the cosmic microwave background, the faint afterglow of the Big Bang. This approach gives us a snapshot of the early universe and suggests a specific expansion rate. The other method focuses on nearby objects like Cepheid variable stars and supernovae, which act as cosmic yardsticks. These observations, however, point to a faster expansion rate than what the early universe data predicts. So, why does this matter? Well, the expansion rate of the universe is a cornerstone of cosmology. It helps us understand everything from the age of the universe to the fate of galaxies. If our measurements don't align, it could mean there's something fundamental we're missing, perhaps a new force, an unknown particle, or even a flaw in our current understanding of gravity. The Virgo Supercluster plays a key role in this mystery. Observations within this region have provided critical data for the local measurements of the expansion rate. Yet, even here, the numbers don't quite add up. This has led scientists to question whether the supercluster's unique environment, its dense concentration of galaxies and dark matter, might be influencing the results in ways we don't yet understand. The Hubble tension isn't just a technical disagreement. It's a challenge to the standard model of cosmology, which has been remarkably successful in explaining the universe so far. If this tension persists, it could force us to rethink some of the most fundamental aspects of physics. Are we on the brink of a major breakthrough, or is there a simpler explanation waiting to be uncovered? As we continue to explore the Virgo Supercluster and beyond, the Hubble tension reminds us that even the most well-established theories can be called into question. It's a humbling reminder that the universe still holds many secrets, and each mystery we solve often leads to even deeper questions. Next, we'll explore another high-energy puzzle within the Virgo Supercluster, the massive cold fronts observed in its intracluster medium. These cosmic phenomena reveal a turbulent history that's as fascinating as it is mysterious. Now, let's shift our focus to a phenomenon that's as dramatic as it is mysterious, the cold fronts of the Virgo cluster. These aren't your typical weather patterns. They're colossal waves of cooler gas moving through the superheated intracluster medium, the vast sea of plasma that fills the space between galaxies in the cluster. Imagine a cosmic tsunami, but instead of water, it's a wave of gas millions of degrees cooler than its surroundings, stretching across hundreds of thousands of light years. These cold fronts are no small-scale events. They're some of the most energetic structures ever observed in the universe, and their discovery has opened a new window into the violent history of the Virgo cluster. But how do they form? Scientists believe these fronts are the result of massive collisions between galaxies or smaller galaxy groups merging into the cluster. As these cosmic giants slam into one another, they create shock waves that ripple through the intracluster medium, carving out these cooler, denser regions. What makes these cold fronts so fascinating is what they reveal about the cluster's past. Each front is like a fossilized record of ancient cosmic collisions, preserving the energy and turbulence of events that happened billions of years ago. By studying their size, shape, and movement, astronomers can piece together a timeline of the Virgo cluster's evolution, uncovering how it grew into the massive structure we see today. But there's more to these cold fronts than just their history. They also play a crucial role in shaping the cluster's present and future. The cooler gas in these fronts can condense and form new stars, influencing the growth of galaxies within the cluster. At the same time, the energy released by these collisions heats the surrounding gas, preventing it from cooling too quickly and collapsing into new structures. It's a delicate balance, one that highlights the dynamic and ever-changing nature of the universe. The cold fronts of the Virgo cluster are a reminder that even in the vastness of space, nothing is static. Every collision, every shockwave leaves its mark, shaping the cosmos in ways we're only beginning to understand. As we continue to study these phenomena, we're not just uncovering the secrets of the Virgo cluster, we're gaining new insights into the forces that drive the evolution of the universe itself. Next, we'll turn our attention to one of the most iconic objects in the Virgo supercluster, the supermassive black hole at the heart of the M87 galaxy. This cosmic giant has captivated scientists and the public alike, and its mysteries are as profound as they are awe-inspiring. Now, let's journey to the heart of the M87 galaxy, where one of the most enigmatic objects in the universe resides, the supermassive black hole. This cosmic giant made history in 2019 when scientists captured the first ever image of a black hole, revealing a glowing ring of light surrounding a dark, shadowy core. This groundbreaking achievement not only confirmed predictions made by Einstein's theory of general relativity, but also gave us an unprecedented glimpse into the extreme physics at play in the universe's most mysterious regions. What makes this black hole so extraordinary isn't just its size. It's estimated to weigh in at a staggering 6.5 billion times the mass of our Sun, but also its behavior. Unlike many supermassive black holes, the one in M87 is incredibly active, launching a powerful jet of particles and radiation that stretches for thousands of light years into space. This jet, traveling at nearly the speed of light, is one of the most energetic phenomena ever observed, and its origins remain a puzzle. Scientists believe the jet is powered by the black hole's intense gravitational pull, which accelerates matter to incredible speeds as it spirals inward. But not all of this material falls into the black hole. Some of it is funneled along magnetic field lines and blasted outward in opposite directions, creating the jet we see. The exact mechanisms behind this process, however, are still not fully understood. Why does some matter escape while the rest is consumed? What role do magnetic fields play in shaping the jet structure? These are questions that continue to challenge our understanding of black hole physics. Adding to the mystery is the black hole's environment. M87 is located in the Virgo cluster, a dense region of galaxies where interactions and collisions are common. Could these cosmic encounters have influenced the black hole's formation or its jet? Some researchers speculate that the black hole's unusual activity might be linked to its history, perhaps shaped by past mergers or the accretion of vast amounts of gas and dust. Studying this black hole isn't just about solving local mysteries, it's about unlocking the secrets of the universe itself. Black holes like the one in M87 are thought to play a crucial role in the evolution of galaxies, influencing star formation and the distribution of matter on cosmic scales. By understanding how this black hole formed and behaves, we gain insights into the forces that shape the cosmos. As we continue to observe and analyze this enigmatic object, one thing is clear. The supermassive black hole in M87 is more than just a scientific curiosity. It's a window into the extreme and dynamic nature of the universe. Next, we'll explore another puzzling aspect of the Virgo Supercluster, the missing satellite galaxies around the Virgo cluster. Why are there fewer of these small galaxies than our models predict? And what does this tell us about the role of dark matter in shaping the cosmos? Now, shifting our gaze to the outskirts of the Virgo cluster, we encounter a cosmic puzzle that has left astronomers scratching their heads: the mystery of the missing satellite galaxies. According to our current understanding of galaxy formation, large galaxies like those in the Virgo cluster should be surrounded by a swarm of smaller satellite galaxies, much like moons orbiting a planet. Yet, when scientists count these satellites, the numbers don't add up. There are far fewer than what our models predict. So, where are they? One leading theory points to the role of dark matter. In the standard model of cosmology, dark matter is thought to form a kind of cosmic scaffolding, providing the gravitational pull needed to gather gas and dust into galaxies. Simulations suggest that this dark matter should also create numerous small clumps, which would eventually become satellite galaxies. But in the Virgo cluster, many of these expected satellites are simply missing. Could dark matter behave differently than we think, or are these satellites hiding in plain sight? Some researchers propose that these satellite galaxies might be too faint or diffuse to detect with current telescopes. Others suggest that interactions within the cluster, such as gravitational tugs from larger galaxies or collisions with other satellites, could have disrupted or destroyed them over time. It's also possible that the intense environment of the Virgo cluster, with its high density of galaxies and hot gas, has stripped away the material needed for these smaller galaxies to form or survive. Another intriguing possibility is that our understanding of dark matter itself might need revision. Perhaps dark matter particles interact in ways we haven't yet discovered, affecting how satellite galaxies form and evolve. Alternatively, the missing satellites could be a clue that our models of galaxy formation are incomplete, missing key pieces of the puzzle that govern how galaxies grow and interact in dense environments like the Virgo cluster. This mystery isn't just about counting galaxies, it's about understanding the fundamental forces that shape the universe. The missing satellites challenge our assumptions about dark matter, galaxy formation, and the complex interplay of cosmic forces. Solving this puzzle could shed light on the nature of dark matter itself and help us refine our models of how galaxies, both large and small, come to be. As we continue to explore the Virgo cluster, one thing is certain: the missing satellites are a reminder that even in the vastness of space, there are still countless mysteries waiting to be uncovered. Next, we'll turn our attention to another enigmatic feature of the Virgo cluster: the massive radio halo that surrounds it. What causes this vast, invisible glow, and what does it tell us about the high-energy processes at work in this cosmic neighborhood? Now, let's dive into another fascinating mystery of the Virgo cluster: the enigmatic radio halo that envelops it. Imagine a vast, invisible glow stretching across millions of light years, emitting radio waves that hint at unseen cosmic forces at work. This radio halo is one of the largest and most puzzling features of the Virgo cluster, and its origins remain a subject of intense debate among astronomers. At its core, a radio halo is a diffuse region of radio emission that surrounds galaxy clusters, and the one in the Virgo cluster is no ordinary example. It's thought to be generated by high-energy particles like cosmic rays spiraling through magnetic fields. But how these particles are accelerated to such extreme energies and what maintains the magnetic fields on such a colossal scale are questions that continue to baffle scientists. One leading theory suggests that the radio halo is fueled by the turbulent environment of the Virgo cluster itself. As galaxies move through the cluster, they create shock waves and collisions which could accelerate particles to near light speeds. These particles, in turn, interact with the cluster's magnetic fields, producing the radio waves we detect. It's a cosmic dance of energy and magnetism, but the exact mechanisms behind it are still unclear. Another possibility is that the radio halo is linked to the cluster's dark matter. Some researchers propose that dark matter interactions could generate the necessary energy to power the halo, though this remains speculative. Alternatively, the halo might be a remnant of past cosmic events, such as the merger of smaller galaxy clusters, which could have injected vast amounts of energy into the system. What makes this phenomenon even more intriguing is its sheer scale. The radio halo extends far beyond the visible galaxies of the Virgo cluster, suggesting that its influence reaches into the very fabric of the cosmic web. Studying it could provide clues about how galaxy clusters evolve and how energy is distributed across the universe. As we continue to probe this mysterious glow, one thing is certain: the radio halo of the Virgo cluster is a testament to the dynamic and energetic nature of the cosmos. It challenges us to rethink our understanding of particle acceleration, magnetic fields, and the interplay of forces that shape the universe on the largest scales. Next, we'll explore another cosmic oddity within the Virgo Supercluster, the strange alignment of galaxies that seems to defy randomness. What could be causing this peculiar pattern, and what does it reveal about the structure of the universe? Now, shifting our gaze to another cosmic puzzle, we encounter the strange alignment of galaxies within the Virgo Supercluster. Picture this: instead of galaxies scattered randomly across the sky, they appear to line up in a way that defies the laws of chance. This peculiar pattern has left astronomers scratching their heads, wondering what unseen forces could be orchestrating such a cosmic ballet. At first glance, one might assume that galaxies are distributed randomly throughout the universe like stars in the night sky. But observations of the Virgo Supercluster reveal something far more intriguing. Galaxies within this vast region seem to align along specific axes, forming what scientists call filaments or walls of galaxies. These structures stretch across millions of light years, creating a web-like pattern that hints at a deeper, underlying order. One leading theory suggests that this alignment is tied to the large-scale structure of the universe itself. The cosmic web, a vast network of dark matter and gas, is thought to guide the formation and distribution of galaxies. In this model, galaxies form along the densest threads of the web, pulled together by gravity over billions of years. The Virgo Supercluster, as part of this cosmic tapestry, may simply be following the blueprint laid out by the web's intricate design. Another possibility is that the alignment is influenced by the supercluster's dynamic history. Over time, galaxies within the Virgo Supercluster have interacted, collided, and merged, shaping their trajectories and orientations. These interactions could have caused galaxies to align along specific directions, creating the patterns we observe today. It's a cosmic domino effect where the movements of one galaxy influence the paths of its neighbors. But why does this matter? The alignment of galaxies offers a unique window into the forces that shape the universe on the largest scales. By studying these patterns, scientists can test theories about dark matter, gravity, and the evolution of cosmic structures. It also raises profound questions about the nature of the universe itself. Is this alignment a sign of some deeper cosmic order, or is it simply a quirk of how galaxies form and evolve? As we continue to map the Virgo Supercluster and beyond, the strange alignment of galaxies remains a tantalizing mystery. It challenges our understanding of randomness and order in the cosmos, reminding us that the universe is far more interconnected than we might imagine. Next, we'll turn our attention to another fascinating feature of the Virgo cluster, the faint glow of stars between galaxies, known as intracluster light. What secrets does this ghostly illumination hold, and what can it tell us about the history of galactic interactions? Now, let's step into the shadowy realm of the Virgo cluster's intracluster light, a faint, ghostly glow that lingers between galaxies like cosmic whispers from the past. This mysterious illumination isn't tied to any single galaxy, but instead fills the vast spaces between them, offering a haunting glimpse into the cluster's turbulent history. So, what exactly is intracluster light? Imagine the aftermath of a cosmic collision. When galaxies interact or merge, their gravitational forces can rip stars from their homes, flinging them into the void between galaxies. These orphaned stars, no longer bound to any single galaxy, drift freely, creating a diffuse glow that spans millions of light years. This is intracluster light, a faint but persistent reminder of the violent encounters that have shaped the Virgo cluster over billions of years. But why does this matter? Intracluster light acts as a cosmic fossil, preserving clues about the cluster's evolution. By studying its distribution and brightness, astronomers can piece together the history of galactic interactions within the Virgo cluster. For instance, the presence of intracluster light suggests that the cluster has experienced numerous mergers and collisions, with galaxies tearing each other apart and scattering stars into the intergalactic void. It's like reading the scars of a cosmic battlefield, where the faint glow tells the story of galaxies that once clashed and reshaped the cluster's structure. One of the most intriguing aspects of intracluster light is what it reveals about dark matter. The distribution of this faint glow often aligns with the cluster's dark matter halo, suggesting that dark matter plays a key role in shaping the paths of these orphaned stars. By mapping the intracluster light, scientists can infer the distribution of dark matter, offering a new way to study this elusive substance that makes up most of the universe's mass. But the mysteries don't end there. Intracluster light also raises questions about the nature of stars themselves. Are these orphaned stars different from those still bound to galaxies? Do they age differently in the harsh environment of intergalactic space? These are questions that astronomers are still working to answer as they continue to probe the faint glow for clues. As we peer deeper into the Virgo cluster's intracluster light, we're reminded of the interconnectedness of the cosmos. This faint glow, often overlooked, holds the key to understanding the dynamic processes that shape galaxy clusters. It's a testament to the universe's complexity, where even the spaces between galaxies are filled with stories waiting to be uncovered. Next, we'll explore another enigmatic phenomenon within the Virgo Supercluster, fast radio bursts. These fleeting, high-energy signals have puzzled scientists for years. What could be causing these mysterious cosmic flashes, and what do they tell us about the universe? Now, let's turn our attention to one of the most baffling cosmic signals ever detected: fast radio bursts, or FRB. These fleeting, high-energy bursts of radio waves last just milliseconds, but they pack an incredible amount of power, equivalent to what the Sun emits in decades. First discovered in 2007, FRBs have since become one of the most tantalizing mysteries in modern astronomy, and the Virgo Supercluster is no stranger to these enigmatic signals. So, what exactly are fast radio bursts? Imagine a flash of radio light so intense that it can be detected across billions of light years, yet so brief that it vanishes almost as quickly as it appears. These bursts are incredibly rare and unpredictable, making them difficult to study. But when they are detected, they leave astronomers scrambling to understand their origins. Within the Virgo Supercluster, FRBs have been observed with peculiar characteristics that defy easy explanation. One of the leading theories suggests that FRBs could originate from highly magnetized neutron stars known as magnetars. These dense, rapidly spinning stellar remnants are capable of producing immense magnetic fields, which could generate the intense bursts of energy we observe. In fact, in 2020, astronomers detected an FRB from a magnetar within our own galaxy, providing strong evidence for this theory. However, not all FRBs fit this explanation, leaving room for other possibilities. Another intriguing idea is that FRBs could be the result of cataclysmic cosmic events, such as the collision of neutron stars or the collapse of massive stars into black holes. These violent processes could release bursts of energy that travel across the universe, appearing as FRBs when they reach us. Yet, even these explanations don't account for the repeating FRBs that have been observed, which seem to defy the one-time nature of such catastrophic events. And then, of course, there's the more speculative possibility: could FRBs be signals from advanced alien civilizations? While this idea captures the imagination, scientists approach it with caution. The sheer energy required to produce an FRB would far exceed anything humanity is capable of, making it an unlikely but not impossible scenario. For now, this remains a fascinating, if unproven, hypothesis. What makes FRBs even more puzzling is their ability to help us map the universe. As these bursts travel through space, they interact with the cosmic web, the vast network of gas and dark matter that fills the universe. By studying how FRBs are distorted as they pass through this material, astronomers can learn more about the distribution of matter in the cosmos, including within the Virgo Supercluster. Despite the progress made in understanding FRBs, many questions remain. Why do some repeat while others don't? What exactly powers these bursts, and could they hold clues to phenomena we haven't even imagined yet? As astronomers continue to study these mysterious signals, one thing is clear: FRBs are a reminder of how much we still have to learn about the universe. Next, we'll delve into another cosmic mystery within the Virgo Supercluster: the elusive dark matter filaments that are thought to connect galaxies in ways we're only beginning to understand. What role do these invisible threads play in shaping the structure of the universe? Let's find out. Now, let's shift our focus to one of the most elusive and fascinating features of the Virgo Supercluster: the dark matter filaments. These invisible threads are thought to weave through the cosmos, connecting galaxies in a vast, intricate web. While we can't see them directly, their presence is inferred through their gravitational effects on the visible universe. But what exactly are these filaments, and why are they so difficult to study? Dark matter filaments are believed to form the backbone of the cosmic web, the large-scale structure of the universe. They act like highways, guiding the flow of galaxies and gas across immense distances. In the Virgo Supercluster, these filaments are thought to link galaxies together, shaping the cluster's overall structure and influencing how galaxies move and interact. But because dark matter doesn't emit, absorb, or reflect light, detecting these filaments is an enormous challenge. One of the primary methods scientists use to study dark matter filaments is gravitational lensing. This phenomenon occurs when the immense gravity of a massive object, like a galaxy cluster, bends the light from objects behind it. By observing how light is distorted, astronomers can map the distribution of dark matter, including the filaments. However, this technique has its limitations. The distortions are often subtle, and the data can be difficult to interpret, especially in regions where the filaments are faint or spread out. Another approach involves studying the motion of galaxies within the Virgo Supercluster. Since dark matter exerts a gravitational pull, its presence affects how galaxies move. By tracking the velocities of galaxies, researchers can infer the distribution of dark matter and identify where filaments might be located. Yet, this method also comes with challenges. The motions of galaxies are influenced by many factors, including interactions with other galaxies and the cluster's overall gravitational field, making it hard to isolate the effects of dark matter filaments alone. Adding to the complexity, dark matter filaments are not uniform. They vary in density and thickness, and their structure can change over time as the universe evolves. Some filaments may be thick and dense, while others are thin and wispy. This variability makes it even harder to create a clear picture of their role in the Virgo supercluster. Despite these challenges, scientists are making progress. Advanced simulations and new observational techniques are helping to reveal more about these mysterious structures. So, why do dark matter filaments matter? They play a crucial role in the formation and evolution of galaxies and galaxy clusters. By understanding these filaments, we can gain deeper insights into how the universe is structured and how it has changed over billions of years. They also hold clues to the nature of dark matter itself, one of the greatest unsolved mysteries in modern science. As we continue to explore the Virgo supercluster, the study of dark matter filaments reminds us of the hidden forces shaping the cosmos. Next, we'll turn our attention to another intriguing phenomenon, the unusual star formation in dwarf galaxies within the Virgo supercluster. What causes these small galaxies to burst into life in unexpected ways? Let's find out. Now, let's dive into another cosmic mystery that's been puzzling astronomers: the unusual star formation in dwarf galaxies within the Virgo supercluster. These small, faint galaxies are often overlooked, but they hold some of the most surprising secrets about how stars are born. Typically, dwarf galaxies are thought to be quiet, with slow and steady star formation. But in the Virgo supercluster, some of these galaxies are defying expectations, bursting into life with intense and unexpected star-forming activity. What's causing these sudden stellar fireworks? One leading theory points to the environment of the Virgo supercluster itself. Dwarf galaxies here are not isolated. They are surrounded by a sea of larger galaxies, hot gas, and dark matter. As these small galaxies move through the cluster, they can experience intense gravitational forces and interactions with other galaxies. These encounters can compress gas within the dwarf galaxies, triggering sudden bursts of star formation. Imagine a small boat caught in the wake of a massive ship. The turbulence can stir up the water, creating waves. Similarly, the gravitational wake of larger galaxies can stir up gas in dwarf galaxies, igniting new stars. Another factor could be the pressure from the supercluster's intracluster medium, the hot gas that fills the space between galaxies. As dwarf galaxies travel through this high-pressure environment, their gas clouds can be compressed, leading to rapid star formation. Think of it like squeezing a sponge. When pressure is applied, the material inside is forced together, sparking new activity. This process, known as ram pressure, might explain why some dwarf galaxies in the Virgo supercluster are lighting up with new stars. But there's more to the story. Some researchers suggest that collisions between dwarf galaxies could also play a role. When two small galaxies collide, their gas clouds can merge and collapse, creating the perfect conditions for star formation. These collisions might be rare, but in a dense environment like the Virgo supercluster, they could be more common than we think. It's like a cosmic dance when two partners come together. The energy of their movement can set off a spectacular display. Interestingly, not all dwarf galaxies in the Virgo supercluster show this unusual star formation. Some remain quiet while others burst into life. This variation suggests that the cluster's environment isn't the only factor at play. The internal properties of the dwarf galaxies, such as their gas content and structure, might also influence whether they experience these star-forming bursts. It's a complex interplay of external and internal forces, making this phenomenon even more intriguing. So, why does this matter? Understanding star formation in dwarf galaxies can give us clues about how galaxies evolve, especially in dense environments like the Virgo supercluster. These small galaxies might seem insignificant, but they're like cosmic laboratories, revealing processes that could shape the universe on a larger scale. They also remind us that even the smallest objects in the cosmos can hold big surprises. As we continue to explore the Virgo supercluster, the unusual star formation in dwarf galaxies challenges our assumptions and opens new questions about the forces driving cosmic evolution. Next, we'll turn our attention to another mystery, the surprisingly low number of supernovae observed in the Virgo cluster. Why are these explosive events so rare here, and what does it mean for our understanding of stellar life cycles? Let's find out. Now, let's shift our gaze to another cosmic puzzle, the Virgo cluster's missing supernova. Supernova, the explosive deaths of massive stars, are some of the most dramatic events in the universe. They light up the cosmos, outshining entire galaxies for a brief moment, and leave behind remnants that shape the evolution of their surroundings. Yet, in the Virgo cluster, these spectacular events seem to be vanishingly rare. Astronomers have observed far fewer supernovae here than expected, and this discrepancy has sparked a wave of curiosity and debate. One possible explanation is that some supernovae in the Virgo cluster are simply being missed. The cluster is a crowded and chaotic environment filled with gas, dust, and countless galaxies. This dense setting could obscure supernova, making them harder to detect. Imagine trying to spot a firework in a thick fog. It's not that the firework isn't there, but the conditions make it difficult to see. Similarly, the Virgo cluster's dusty environment might be hiding some of these explosive events from our telescopes. Another intriguing possibility is that the stellar populations in the Virgo cluster are different from what we see elsewhere. Supernova occur when massive stars reach the end of their lives, but if the cluster has fewer of these massive stars, it could explain the lower number of supernova. Perhaps the conditions in the Virgo cluster favor the formation of smaller stars which don't end their lives in such dramatic fashion. It's like a forest where most trees are saplings. There just aren't enough old, towering trees to produce the occasional thunderous crash. There's also the chance that supernova in the Virgo cluster are happening, but in ways we don't fully understand. For instance, some supernova might be failed explosions, where the star collapses into a black hole without the usual bright display. These events would be much harder to detect, leaving astronomers with fewer clues to work with. It's a reminder that even the most violent cosmic events can sometimes slip under our radar. So, why does this matter? Supernovae play a crucial role in the life cycle of galaxies. They scatter heavy elements into space, seeding the cosmos with the building blocks for new stars, planets, and even life. If supernovae are indeed rarer in the Virgo cluster, it could have profound implications for how galaxies here evolve. Are they forming fewer heavy elements? Are their stellar populations aging differently? These are questions that keep astronomers up at night. As we piece together the mystery of the missing supernova, we're reminded that even the most well-studied regions of the universe can still surprise us. The Virgo cluster, with its dense environment and complex dynamics, continues to challenge our understanding of stellar life and death. Next, we'll explore another enigma, the ultra-compact dwarf galaxies that defy our expectations of what a galaxy should be. What makes these tiny, dense objects so unique, and what secrets do they hold about the cosmos? Let's find out. Now, let's turn our attention to a cosmic oddity that challenges everything we thought we knew about galaxies: ultra-compact dwarf galaxies. Nestled within the Virgo Supercluster, these tiny yet incredibly dense objects are unlike anything else in the universe. Imagine a galaxy so small it could fit within the span of our Milky Way's central bulge, yet packed with millions of stars. These ultra-compact dwarfs are so peculiar that they defy traditional galaxy classifications, leaving astronomers scratching their heads. What makes these galaxies so unusual? For starters, their size is baffling. Ultra-compact dwarf galaxies are typically only a few hundred light-years across, making them far smaller than even the tiniest known dwarf galaxies. Yet, despite their diminutive size, they contain a staggering number of stars, sometimes as many as 100 million. This extreme density means that if you were to stand on a planet within one of these galaxies, the night sky would be ablaze with stars, far more densely packed than anything we see from Earth. But the mystery doesn't end there. Ultra-compact dwarf galaxies also have properties that blur the line between galaxies and star clusters. For example, they often contain old stellar populations, similar to globular clusters, but their masses and internal dynamics are more akin to those of much larger galaxies. This has led to intense debates about their origins. Are they the remnants of larger galaxies that were stripped of their outer stars through violent interactions? Or could they be the result of mergers between smaller star clusters, somehow growing dense enough to resemble galaxies? One leading theory suggests that ultra-compact dwarf galaxies are the surviving cores of once larger galaxies that were torn apart by the gravitational forces within the Virgo Supercluster. Picture a massive galaxy wandering too close to the cluster's center, where the pull of gravity is strongest. Over time, its outer layers of stars and gas are ripped away, leaving behind only its dense core. This process, known as tidal stripping, could explain why these objects are so compact and why they're often found near the centers of galaxy clusters. Another possibility is that ultra-compact dwarf galaxies formed through a completely different process, perhaps as dense star clusters that somehow accumulated enough mass to behave like galaxies. This would challenge our understanding of how galaxies form and evolve, suggesting that there's more than one path to creating these cosmic structures. What's clear is that ultra-compact dwarf galaxies are a reminder of how much we still have to learn about the universe. They don't fit neatly into our existing categories, forcing us to rethink what defines a galaxy. Are they a new class of object altogether, or simply an extreme version of something we already know? As we continue to study these enigmatic structures, they may hold the key to unlocking new insights into the complex processes that shape the cosmos. With their strange properties and mysterious origins, ultra-compact dwarf galaxies are a testament to the endless surprises hidden within the Virgo Supercluster. Next, we'll explore another piece of the cosmic puzzle, the Virgo Cluster's cosmic web, and how this vast network of galaxies and dark matter shapes the evolution of the universe. What secrets does this intricate structure hold? Let's dive in. Now, let's unravel one of the most fascinating aspects of the Virgo Supercluster, the cosmic web. This vast, intricate network of galaxies, gas, and dark matter stretches across the universe, connecting clusters like Virgo in a delicate tapestry of cosmic architecture. Picture it as a spider's web, but on a scale so immense that it defies imagination. The Virgo cluster sits at the heart of this web, acting as a central hub where galaxies and matter converge, shaping the destiny of everything within its reach. The cosmic web isn't just a random arrangement of galaxies. It's a carefully structured framework that governs how galaxies form, evolve, and interact. At its core are filaments, thread-like structures made of dark matter and gas that stretch across billions of light years, connecting clusters like Virgo to other superclusters. These filaments act as cosmic highways, guiding the flow of matter and energy throughout the universe. Galaxies, including our own Milky Way, are strung along these filaments like beads on a string, drawn together by the irresistible pull of gravity. But what makes the Virgo cluster's position in the cosmic web so significant? For one, its location at the intersection of multiple filaments makes it a gravitational powerhouse. The cluster's immense mass pulls in galaxies and gas from surrounding regions, funneling them into its core. This process not only fuels the growth of the cluster itself, but also influences the evolution of galaxies within it. Galaxies that fall into the Virgo cluster are often transformed by the intense gravitational forces, leading to collisions, mergers, and bursts of star formation. The cosmic web also plays a crucial role in distributing matter throughout the universe. Without this structure, galaxies would be scattered randomly, and the universe as we know it would look entirely different. The filaments of the web act as conduits, channeling gas and dark matter into clusters like Virgo, where they can coalesce into new stars and galaxies. This continuous flow of matter ensures that the universe remains dynamic and ever-changing, with clusters like Virgo serving as cosmic hubs of activity. One of the most intriguing aspects of the cosmic web is its connection to dark matter. Though invisible, dark matter forms the backbone of the web, providing the gravitational scaffolding that holds everything together. Without it, the filaments would collapse and the web would unravel. Studying the Virgo cluster's place within this structure gives us valuable insights into the nature of dark matter and its role in shaping the universe. As we peer deeper into the cosmic web, we begin to see how interconnected everything truly is. The Virgo cluster isn't just an isolated collection of galaxies. It's a vital part of a much larger system, one that influences the evolution of galaxies across vast distances. This intricate network reminds us that the universe is far more complex and interconnected than we often realize. With the cosmic web as our guide, we're ready to explore another layer of the Virgo Supercluster's mysteries, the strange behavior of active galactic nuclei, or AN. These energetic powerhouses found at the hearts of galaxies hold secrets that could reshape our understanding of the universe. What drives their incredible energy output, and what can they tell us about the forces at work in the cosmos? Let's find out. Now, let's turn our attention to one of the most enigmatic features of the Virgo Supercluster, the strange behavior of active galactic nuclei, or AN. These cosmic powerhouses found at the centers of galaxies are among the most energetic objects in the universe. But what exactly makes them so unusual, and what can they tell us about the supermassive black holes that drive them? At the heart of every AGN lies a supermassive black hole, millions or even billions of times more massive than our Sun. These black holes are far from dormant. They are surrounded by swirling disks of gas and dust known as accretion disks. As material spirals into the black hole, it heats up to incredible temperatures, releasing vast amounts of energy in the form of light, X-rays, and even jets of particles that shoot out at nearly the speed of light. This process makes AGNs some of the brightest objects in the universe, outshining entire galaxies. One of the most puzzling aspects of AGNs is their variability. Their brightness can change dramatically over short periods, sometimes in just days or even hours. This rapid flickering suggests that the processes happening near the black hole are incredibly dynamic and chaotic. Scientists believe these fluctuations are tied to the turbulent nature of the accretion disk, where clumps of material collide and interact unpredictably. Studying this variability gives us a glimpse into the extreme conditions near the event horizon of a black hole, where gravity is so strong that not even light can escape. The energy output of AGNs is equally astonishing. Some AGNs emit more energy in a single second than our Sun will produce in its entire lifetime. This energy isn't just radiated as light, it also powers colossal jets that extend far beyond the host galaxy. These jets, made of charged particles, can stretch for millions of light years, carving out vast bubbles in the surrounding intergalactic medium. The Virgo Supercluster is home to several AGNs with such jets, including the famous M87 galaxy, whose black hole was the first ever to be directly imaged. But what does all this activity reveal about supermassive black holes? For one, it shows that these cosmic giants are not just passive objects lurking in the centers of galaxies. They are active participants in shaping their environments, influencing the evolution of galaxies and even entire clusters. The energy released by AGNs can heat up surrounding gas, preventing it from cooling and forming new stars. This process, known as feedback, plays a crucial role in regulating galaxy growth and maintaining the balance of matter in the universe. Moreover, AGNs provide a unique laboratory for testing our understanding of physics under extreme conditions. The intense gravitational fields and relativistic speeds near black holes push the limits of Einstein's theory of general relativity. By studying AGNs, scientists can probe the nature of spacetime itself, uncovering clues about how gravity works in the most extreme environments. As we continue to explore the Virgo Supercluster, the strange behavior of AGNs reminds us just how dynamic and interconnected the universe truly is. These cosmic powerhouses not only illuminate the mysteries of supermassive black holes, but also shape the destiny of galaxies on a grand scale. And with that, we're ready to delve into another layer of the Virgo Supercluster's mysteries, the puzzling absence of intergalactic gas, a phenomenon that challenges our understanding of cosmic matter distribution. Now, shifting our gaze to another cosmic puzzle, we encounter the mystery of the Virgo cluster's missing intergalactic gas. This phenomenon has left scientists scratching their heads as the expected reservoirs of gas between galaxies seem to have vanished. But where did it go, and what does its absence tell us about the dynamics of this massive cluster? Intergalactic gas, often referred to as the intracluster medium, is a crucial component of galaxy clusters. It's the thin, hot gas that fills the spaces between galaxies, acting as a kind of cosmic glue that holds the cluster together. In most clusters, this gas is abundant, making up a significant portion of the cluster's total mass. However, in the Virgo cluster, observations have revealed a surprising shortage of this gas, challenging our understanding of how matter is distributed in the universe. One leading theory suggests that galactic winds might be responsible for this absence. These winds, driven by the intense activity of star formation and supermassive black holes, can blow gas out of galaxies and into the intergalactic space. Over time, this gas could be pushed so far out that it escapes the cluster entirely, leaving behind a noticeable void. This process, known as feedback, is a key mechanism in galaxy evolution, but its effects in the Virgo cluster appear to be unusually pronounced. Another intriguing possibility involves dark matter. While dark matter itself doesn't interact with light or gas, its gravitational influence could play a role in redistributing the intergalactic gas. Some scientists propose that interactions between dark matter and the gas could cause the gas to clump together in unexpected ways or even be expelled from the cluster. This idea is still speculative, but it highlights the complex interplay between visible and invisible matter in shaping the cosmos. The absence of intergalactic gas in the Virgo cluster also has broader implications for our understanding of galaxy clusters. Without this gas, the cluster's ability to retain heat and regulate star formation could be significantly altered. This could explain why some galaxies in the Virgo cluster appear to be aging faster than expected, as the lack of gas prevents the formation of new stars. It's a reminder that even the seemingly empty spaces between galaxies are teeming with activity and mystery. As we continue to study the Virgo cluster, the missing intergalactic gas serves as a stark reminder of how much we still have to learn about the universe. Whether it's galactic winds, dark matter interactions, or some other yet-to-be-discovered process, this phenomenon challenges us to rethink our models of cosmic evolution. And with that, we're ready to explore another layer of the Virgo supercluster's enigma's tidal dwarf galaxies, small but fascinating structures born from the debris of galactic collisions. Now, let's turn our attention to a fascinating cosmic phenomenon that emerges from the chaos of galactic collisions: tidal dwarf galaxies. These peculiar structures are born from the debris left behind when galaxies collide, creating entirely new systems from the wreckage. Unlike typical galaxies, which form from the slow accumulation of gas and dust over billions of years, tidal dwarf galaxies are the cosmic equivalent of a phoenix rising from the ashes, offering a unique window into the dynamic processes that shape our universe. Tidal dwarf galaxies are small, often irregularly shaped, and packed with young, bright stars. They form when the gravitational forces of colliding galaxies pull streams of gas and stars out into long, luminous tails. Over time, these streams can clump together, forming new, self-contained galaxies. What makes them so intriguing is that they are made almost entirely of the leftovers from larger galaxies, challenging our traditional understanding of how galaxies come into existence. In the Virgo Supercluster, tidal dwarf galaxies are surprisingly common, thanks to the cluster's dense environment and frequent galactic interactions. These small galaxies are often found near the edges of larger galaxies or within the vast tidal tails that stretch across the cluster. Their presence provides crucial clues about the history of galactic collisions in the Virgo Supercluster and how these violent events have shaped its current structure. One of the most remarkable aspects of tidal dwarf galaxies is what they reveal about the process of galaxy formation. Unlike larger galaxies, which are dominated by dark matter, tidal dwarf galaxies appear to contain very little of it. This is because they form from the visible matter, gas and stars, that is stripped away during collisions, leaving the dark matter behind. This unique composition makes them a natural laboratory for studying the role of dark matter in galaxy evolution and testing our theories about how galaxies grow and change over time. But tidal dwarf galaxies aren't just scientific curiosities, they also play a role in the larger cosmic ecosystem. Their formation can trigger bursts of star formation, injecting fresh energy and material into their surroundings. In some cases, they may even merge with other galaxies, contributing to the ongoing cycle of galactic evolution. This dynamic interplay highlights the interconnected nature of the universe, where even the smallest structures can have a profound impact. As we study these enigmatic galaxies, we're reminded that the universe is a place of constant change and renewal. Tidal dwarf galaxies, born from destruction, offer a glimpse into the resilience and creativity of cosmic processes. They challenge us to rethink our assumptions about how galaxies form and evolve, and they underscore the importance of studying the Virgo Supercluster as a whole. With that, we're ready to dive into another layer of the Virgo Supercluster's mysteries, unusual X-ray emissions that hint at even more cosmic secrets waiting to be uncovered. Now, let's shift our gaze to a phenomenon that radiates with high energy intrigue: the unusual X-ray emissions emanating from the Virgo cluster. These emissions, detected by powerful telescopes, are not just random bursts of energy, but rather a cosmic fingerprint of the cluster's most extreme and mysterious processes. Unlike the visible light we see from stars and galaxies, X-rays reveal a hidden layer of the universe, one dominated by superheated gas, violent collisions, and the relentless pull of gravity. At the heart of the Virgo cluster lies a vast reservoir of hot gas, heated to temperatures of millions of degrees. This gas, known as the intracluster medium, fills the space between galaxies and glows brightly in X-rays. But what's truly puzzling is the intensity and distribution of these emissions. In some regions, the X-rays are far stronger than expected, hinting at processes that defy our current understanding of astrophysics. Scientists believe these emissions are fueled by the gravitational energy released as galaxies and gas clouds collide, merge, and interact within the cluster. These high-energy events create shock waves that ripple through the intracluster medium, heating the gas and producing the X-rays we observe. One of the most striking features of these X-ray emissions is their ability to map the cluster's dynamic history. By studying the patterns and variations in the X-ray glow, astronomers can trace the paths of galaxies as they move through the cluster, revealing the gravitational forces at work. For example, the X-ray emissions often show sharp edges or cold fronts, where cooler gas clumps collide with the hotter intracluster medium. These features provide a snapshot of the cluster's turbulent past, offering clues about how it has grown and evolved over billions of years. But the mystery deepens when we consider the origins of the gas itself. Where did this superheated material come from, and why does it behave the way it does? Some of the gas is thought to be primordial, left over from the early universe, while other portions may have been stripped from galaxies as they moved through the cluster. The interplay between these sources creates a complex web of energy and matter, one that challenges our understanding of how cosmic structures form and evolve. The X-ray emissions also shed light on the role of supermassive black holes in shaping the cluster. Many galaxies in the Virgo cluster host active galactic nuclei which spew out jets of high-energy particles. These jets can heat the surrounding gas, creating bubbles and cavities in the X-ray glow. By studying these features, scientists can better understand how black holes influence their environments and regulate the growth of galaxies. What makes these X-ray emissions so fascinating is their ability to reveal the invisible forces at work in the universe. They show us a cosmos in constant motion, where gravity, heat, and energy collide in spectacular ways. As we continue to study the Virgo cluster's X-ray emissions, we're not just uncovering the secrets of this one region, we're gaining insights into the high-energy processes that shape the entire universe. With that, we're ready to explore another layer of the Virgo cluster's mysteries, the enigmatic dynamics of its core, where galaxies and dark matter dance in a cosmic ballet. Now, let's venture deeper into the heart of the Virgo cluster, where the core holds secrets that challenge our understanding of cosmic evolution. At the center of this vast assembly of galaxies lies a region of extraordinary activity, dominated by some of the most massive and enigmatic galaxies in the universe. These central galaxies, often referred to as the brightest cluster galaxies, are not just passive inhabitants, they are dynamic players in the cluster's ongoing story. The core of the Virgo cluster is a place of intense gravitational forces, where galaxies are drawn together by the immense pull of dark matter. This gravitational tug of war shapes the behavior of the galaxies, causing them to orbit, collide, and sometimes merge. One of the most striking features of the core is the presence of a giant elliptical galaxy, Messier 87 or M87, which sits at the very center. This galaxy is home to a supermassive black hole, whose influence extends far beyond its immediate surroundings, shaping the entire core region. What makes the core so fascinating is the way it reveals the interplay between galaxies and their environment. The central galaxies are often surrounded by vast halos of stars, gas, and dark matter, creating a complex web of interactions. These interactions can trigger bursts of star formation, fuel the growth of supermassive black holes, and even strip gas and stars from smaller galaxies as they pass through the core. This process, known as galactic cannibalism, plays a key role in shaping the evolution of the cluster. But the core's mysteries don't end there. Observations have revealed that the central galaxies are not randomly distributed. They tend to align in specific patterns, suggesting the presence of large-scale structures within the cluster. These structures, shaped by the gravitational influence of dark matter, act as cosmic highways, guiding the movement of galaxies and influencing their evolution over billions of years. The behavior of the core also provides clues about the cluster's history. For example, the presence of cool cores, regions where the intracluster gas is cooler and denser, suggests that the cluster has experienced periods of relative calm. In contrast, disturbed cores, marked by chaotic gas motions and irregular structures, indicate a history of violent interactions and mergers. By studying these features, astronomers can piece together the cluster's past and predict its future evolution. One of the most intriguing aspects of the core is its connection to dark matter. The distribution of galaxies and gas in the core is thought to trace the underlying dark matter structure, providing a unique window into this invisible component of the universe. By mapping the core's dynamics, scientists can test theories about the nature of dark matter and its role in shaping cosmic structures. As we explore the mysteries of the Virgo cluster's core, we're not just uncovering the secrets of this one region, we're gaining insights into the fundamental processes that govern the evolution of galaxy clusters throughout the universe. The core serves as a cosmic laboratory where the forces of gravity, dark matter, and high-energy physics collide in ways that challenge and expand our understanding of the cosmos. With that, we're ready to turn our attention to another enigma: the surprising absence of dwarf galaxies in the Virgo cluster, a puzzle that continues to baffle astronomers. Now, shifting our gaze to another cosmic puzzle, we encounter the curious case of the Virgo cluster's missing dwarf galaxies. Dwarf galaxies, the smaller and fainter cousins of larger galaxies like our Milky Way, are expected to be abundant in galaxy clusters. Yet, when astronomers look at the Virgo cluster, they find far fewer of these tiny galaxies than current models predict. This discrepancy has sparked a lively debate among scientists, raising questions about our understanding of galaxy formation and the role of dark matter. Theories about this missing population often point to the influence of dark matter. According to the standard model of cosmology, dark matter forms a vast, invisible scaffold that guides the formation and distribution of galaxies. In the Virgo cluster, this dark matter framework should host a large number of dwarf galaxies. However, many of these galaxies seem to be absent. One possibility is that they are simply too faint to detect with current telescopes, blending into the background noise of the cluster. Another theory suggests that the intense gravitational forces within the cluster may have disrupted or destroyed these fragile galaxies, stripping away their stars and gas over billions of years. Another intriguing explanation involves the interactions between dwarf galaxies and their environment. As these small galaxies move through the cluster, they can be torn apart by tidal forces or stripped of their gas by the hot intracluster medium. This process, known as galactic harassment, could leave behind only faint remnants or completely dissolve the galaxies, making them invisible to our instruments. Additionally, some dwarf galaxies may have merged with larger galaxies, effectively disappearing from the observable population. Observational limitations also play a role in this mystery. Detecting dwarf galaxies, especially those that are faint or distant, is a significant challenge. Many of these galaxies are so dim that they can only be spotted with the most advanced telescopes, and even then, only under ideal conditions. The dense environment of the Virgo cluster, with its bright central galaxies and glowing intracluster gas, further complicates the search, potentially obscuring these elusive objects. Despite these challenges, astronomers are making progress. New observational techniques and upcoming telescopes, like the James Webb Space Telescope and the Vera C. Rubin Observatory, promise to shed light on this mystery. By peering deeper into the cluster and capturing more detailed images, scientists hope to uncover the missing dwarf galaxies and better understand their role in the cosmic ecosystem. The mystery of the Virgo cluster's missing dwarf galaxies is more than just a cosmic curiosity. It's a window into the complex interplay of dark matter, gravity, and galaxy evolution. As we continue to explore this enigma, we edge closer to unraveling the secrets of how galaxies form, evolve, and interact within the vast tapestry of the universe. With that, let's turn our attention to another fascinating phenomenon: the complex and poorly understood magnetic fields that permeate the Virgo cluster. Now, let's venture into another layer of the Virgo cluster's mysteries: its enigmatic magnetic fields. These invisible forces weave through the vast expanse of the cluster, shaping the behavior of galaxies and the hot gas that fills the space between them. Yet, despite their significance, the origins and full extent of these magnetic fields remain one of the most puzzling aspects of the Virgo Supercluster. Magnetic fields in space are not like the simple bar magnets we're familiar with on Earth. Instead, they are vast, tangled webs of energy that stretch across millions of light years. In the Virgo cluster, these fields are thought to be generated by the motion of charged particles within the intracluster medium, the superheated gas that permeates the cluster. As galaxies move through this gas, they can drag magnetic fields along with them, creating complex patterns that are difficult to map and even harder to explain. One of the biggest challenges in studying these magnetic fields is their faintness. Unlike stars or galaxies, magnetic fields don't emit light. Instead, they reveal themselves indirectly through their influence on charged particles and the polarization of light. Astronomers use specialized instruments to detect these subtle effects, but even then, the data is often incomplete or difficult to interpret. This has led to a wide range of theories about how these fields form and evolve. Some scientists believe that the magnetic fields in the Virgo cluster were seeded during the early universe when the first stars and galaxies were forming. These primordial fields could have been amplified over billions of years by the motion of gas and galaxies within the cluster. Others suggest that the fields are generated locally by the turbulent activity of supermassive black holes or the collision of galaxies. These violent events can produce shock waves that ripple through the intracluster medium, potentially creating or strengthening magnetic fields in their wake. The impact of these magnetic fields on galactic evolution is profound. They can influence the flow of gas within galaxies, affecting star formation and the growth of supermassive black holes. They also play a role in shaping the structure of the intracluster medium, guiding the movement of gas and even influencing the trajectories of galaxies themselves. In some cases, magnetic fields may help to stabilize the cluster, preventing the gas from cooling too quickly and collapsing into new stars. In others, they might contribute to the chaotic environment that disrupts smaller galaxies. Despite their importance, much about these magnetic fields remains unknown. How strong are they, and how do they vary across the cluster? What role do they play in the life cycles of galaxies? And how do they interact with other forces like gravity and dark matter? These are questions that astronomers are still working to answer. As we continue to explore the Virgo cluster, new technologies and observational techniques are bringing us closer to understanding these mysterious magnetic fields. Instruments like the Square Kilometre Array, a next-generation radio telescope, promise to provide unprecedented insights into their structure and behavior. By unraveling this cosmic puzzle, we may gain a deeper understanding of how magnetic fields shape the universe on the largest scales. With this in mind, let's turn our attention to the final phenomenon on our list: the unusual rotation curves of galaxies within the Virgo cluster, which challenge our understanding of gravity and dark matter. Now, shifting our gaze to the final mystery on our list, we encounter a phenomenon that has left astronomers scratching their heads: the unusual rotation curves of galaxies within the Virgo cluster. These curves, which describe how stars and gas move around the centers of galaxies, defy our current understanding of gravity and dark matter, presenting a cosmic puzzle that could reshape our view of the universe. In most galaxies, including our own Milky Way, stars and gas orbit the galactic center in a way that follows predictable patterns based on the laws of gravity. The farther a star is from the center, the slower it should move, much like planets in our solar system. However, observations of galaxies in the Virgo cluster reveal something entirely different. Instead of slowing down, stars and gas at the outer edges of these galaxies move at speeds that are far too fast to be explained by the visible matter alone. This discrepancy suggests the presence of something invisible: dark matter exerting a gravitational pull. But here's where it gets even more intriguing. While dark matter is the leading explanation for these unusual rotation curves, the behavior of galaxies in the Virgo cluster doesn't always align with predictions. Some galaxies show rotation curves that are even more extreme, with outer regions spinning faster than expected, while others exhibit patterns that don't fit neatly into existing models. This inconsistency has led scientists to question whether our understanding of dark matter is complete, or if there's something else at play. One possibility is that the unique environment of the Virgo cluster is influencing these rotation curves. The cluster is a dense, dynamic region filled with galaxies, hot gas, and magnetic fields, all interacting in complex ways. These interactions could be altering the distribution of dark matter or even creating additional forces that affect how galaxies rotate. Alternatively, some researchers have proposed modifications to the laws of gravity itself, suggesting that our current theories might need revising to account for these anomalies. The implications of these unusual rotation curves extend far beyond the Virgo cluster. If our understanding of gravity or dark matter is incomplete, it could have profound consequences for cosmology as a whole. Dark matter is a cornerstone of our current model of the universe, helping to explain everything from the formation of galaxies to the large-scale structure of the cosmos. Any revisions to this model could ripple through our understanding of the universe's history and future. As astronomers continue to study these perplexing rotation curves, new tools and techniques are offering fresh insights. Observations from advanced telescopes combined with sophisticated computer simulations are helping to unravel the complex interplay of forces at work in the Virgo cluster. Each discovery brings us closer to understanding whether these anomalies are a quirk of the cluster's environment or a sign of deeper, more fundamental truths about the universe. This brings us to the end of our journey through the 25 unexplained phenomena of the Virgo Supercluster. Each mystery we've explored, from missing dark matter to enigmatic magnetic fields, and now these puzzling rotation curves, challenges our understanding of the cosmos and reminds us how much we have yet to learn. As we continue to probe the depths of space, these mysteries not only inspire curiosity, but also drive the quest for knowledge that defines our exploration of the universe. Now, as we venture into the broader implications of these cosmic mysteries, let's turn our attention to a force that shapes the very fabric of the universe: dark energy. This enigmatic force, which drives the accelerated expansion of the cosmos, may also play a significant role in the behavior and structure of the Virgo supercluster. While dark energy is often discussed on the scale of the entire universe, its influence on smaller cosmic structures like superclusters is a topic of growing interest and debate. Dark energy is thought to counteract the pull of gravity, causing galaxies and clusters to move apart at an ever-increasing rate. In the context of the Virgo supercluster, this could mean that dark energy is subtly influencing the way galaxies interact and evolve within this vast cosmic web. For instance, as the supercluster expands, the gravitational bonds between galaxies may weaken, altering their trajectories and potentially affecting phenomena like the unusual rotation curves we've just explored. Some scientists speculate that dark energy could even contribute to the distribution of dark matter, reshaping the invisible scaffolding that holds galaxies together. But the role of dark energy in the Virgo supercluster isn't just about expansion, it's also about balance. The supercluster is a dynamic environment where the gravitational pull of dark matter and the repulsive force of dark energy are in constant tension. This interplay could explain some of the anomalies we've observed, such as the missing baryons or the strange alignment of galaxies. For example, if dark energy is causing the supercluster to stretch and thin out, it might be dispersing the gas and matter that would otherwise be detectable, leaving behind gaps that puzzle astronomers. One of the most intriguing possibilities is that dark energy could be influencing the formation and evolution of large-scale structures within the supercluster. The cosmic web, the intricate network of filaments and voids that connects galaxies, may be shaped not only by gravity but also by the subtle push of dark energy. This could lead to the formation of unusual features like the massive radio halos or the cold fronts we've discussed earlier. By altering the density and distribution of matter, dark energy might be creating conditions that give rise to these mysterious phenomena. However, studying dark energy's role in the Virgo supercluster is no easy task. Unlike dark matter, which can be inferred through its gravitational effects, dark energy is far more elusive. Its influence is most apparent on the largest scales, making it challenging to detect its impact within a single supercluster. Yet, advancements in observational technology, such as more powerful telescopes and detailed simulations, are beginning to shed light on this cosmic puzzle. By mapping the distribution of galaxies and measuring their movements with unprecedented precision, scientists hope to uncover clues about how dark energy shapes the Virgo Supercluster and, by extension, the universe as a whole. As we continue to explore the mysteries of the Virgo Supercluster, the role of dark energy remains a tantalizing question. Its influence, though subtle, could hold the key to understanding not only the anomalies we've observed but also the broader forces that govern the cosmos. And with each new discovery, we move closer to unraveling the secrets of this enigmatic force and its impact on the universe we call home. As we look ahead, the future of observing the Virgo Supercluster is brimming with promise, thanks to a new generation of telescopes and missions poised to revolutionize our understanding of this cosmic region. These cutting-edge tools are designed to peer deeper into the universe than ever before, offering unprecedented clarity and detail that could finally unravel some of the supercluster's most perplexing mysteries. One of the most anticipated projects is the James Webb Space Telescope, which has already begun to deliver stunning images and data. With its advanced infrared capabilities, Webb can peer through cosmic dust and gas, revealing hidden structures and phenomena within the Virgo Supercluster. This telescope is particularly well-suited to study the faint intracluster light, the elusive dark matter filaments, and even the behavior of supermassive black holes like the one in M87. By capturing light from the earliest stages of the universe, Webb could also provide insights into how the Virgo Supercluster formed and evolved over billions of years. On the ground, the Vera C. Rubin Observatory is set to transform our view of the cosmos. Scheduled to begin full operations in the coming years, this observatory will conduct the legacy survey of space and time, mapping the entire sky in unprecedented detail. Its wide-field camera will allow astronomers to track the movements of galaxies within the Virgo Supercluster with remarkable precision, potentially uncovering clues about the missing baryons, the strange alignment of galaxies, and the distribution of dark matter. The sheer volume of data collected by Rubin could also help identify rare events such as fast radio bursts or unusual star formation in dwarf galaxies that have so far eluded explanation. Meanwhile, the Square Kilometre Array, or SCAR, promises to revolutionize radio astronomy. Once completed, this massive array of radio telescopes will be the most sensitive instrument of its kind, capable of detecting faint signals from the farthest reaches of the universe. Within the Virgo Supercluster, SKA could shed light on the mysterious radio halo, the behavior of active galactic nuclei, and even the cosmic web's magnetic fields. By mapping these phenomena in exquisite detail, SKA could help us understand how dark energy and dark matter interact on a supercluster scale. Closer to home, the Nancy Grace Roman Space Telescope, set to launch in the next decade, will focus on large-scale cosmic structures. Its wide-field instrument will map the distribution of galaxies and dark matter in the Virgo Supercluster, providing critical data on how these structures evolve over time. Roman's observations could also help resolve the Hubble tension by offering independent measurements of the universe's expansion rate, potentially reconciling the discrepancies that have puzzled astronomers for years. These advancements aren't just about collecting data, they're about connecting the dots. By combining observations from multiple telescopes and missions, scientists can build a more comprehensive picture of the Virgo Supercluster. For example, data from Webb and Rubin could be cross-referenced to study the relationship between dark matter and galaxy formation, while SKA and Roman could work together to map the cosmic web's magnetic fields and their influence on galaxy evolution. As these tools come online, they bring with them the potential to solve some of the most enduring mysteries of the Virgo Supercluster. From the missing baryons to the enigmatic radio halo, each unexplained phenomenon represents a piece of the cosmic puzzle waiting to be placed. And with each new discovery, we move closer to understanding not just the Virgo Supercluster, but the fundamental forces that shape our universe. The journey ahead is as exciting as it is challenging. With every observation, every dataset, and every breakthrough, we inch closer to unraveling the secrets of this vast cosmic tapestry. And as we do, we're reminded that the universe is far more complex and wondrous than we ever imagined. As we stand on the brink of these groundbreaking discoveries, it's worth pausing to consider what the mysteries of the Virgo Supercluster truly mean for us as a species. These unexplained phenomena aren't just scientific puzzles, they're windows into the profound questions that have captivated humanity for centuries. What is the nature of the universe? How did it come to be? And what role do we play in this vast, intricate cosmic dance? The Virgo Supercluster, with its missing baryons, enigmatic black holes, and ghostly radio halos, challenges us to rethink our understanding of reality. Each mystery serves as a reminder that the universe is far more complex than our current theories can explain. Yet, it's precisely this complexity that drives our curiosity. The pursuit of knowledge is a deeply human endeavor, one that pushes us to explore the unknown even when the answers remain elusive. At the same time, these cosmic mysteries highlight the limits of our scientific knowledge. For all our advancements, there are still phenomena that defy explanation, forces we can't yet measure, and structures we can't fully comprehend. This isn't a failure, it's an invitation. It reminds us that science is a journey, not a destination. Every unanswered question is an opportunity to learn, to innovate, and to expand the boundaries of what we know. This balance between curiosity and limitation is at the heart of our relationship with the cosmos. On one hand, the Virgo Supercluster inspires awe and wonder, fueling our desire to explore and understand. On the other, it humbles us, reminding us of how much we have yet to discover. It's a duality that defines not just astronomy, but the human experience itself. We are driven by a need to make sense of the world, yet we must also accept that some mysteries may remain unsolved for generations to come. What does this mean for the future of science? It means embracing uncertainty as a fundamental part of the process. It means celebrating the questions as much as the answers, recognizing that every discovery raises new questions in turn. And it means fostering a sense of wonder that transcends generations, inspiring future scientists to continue the search for understanding. Ultimately, the Virgo Supercluster is more than a collection of galaxies and phenomena. It's a mirror reflecting our own curiosity, ambition, and humility. As we continue to explore its mysteries, we're not just uncovering the secrets of the universe, we're also uncovering something about ourselves, our capacity for wonder, our resilience in the face of the unknown, and our unending desire to reach beyond the stars. And in that journey, perhaps we find the most profound truth of all, that the universe is not just something to be understood, but something to be marveled at. As we bring our journey through the Virgo Supercluster to a close, let's take a moment to reflect on the incredible mysteries we've explored. From the missing dark matter in NGC 1052 DF2 to the enigmatic black hole at the heart of M87, each phenomenon has pushed the boundaries of our understanding. The Great Attractor's gravitational pull, the puzzling absence of baryons, and the ghostly ultra-diffuse galaxies all remind us that the universe is far stranger and more complex than we ever imagined. These 25 unexplained phenomena aren't just scientific curiosities, they're profound challenges to our current theories. They force us to question what we think we know about galaxy formation, dark matter, and even the very fabric of space and time. Each mystery is a piece of a larger puzzle, one that may take decades or even centuries to solve. But that's the beauty of science, it thrives on the unknown. As we look to the future, new telescopes and technologies promise to shed light on these cosmic enigmas. Missions like the James Webb Space Telescope and upcoming observatories could unlock secrets hidden within the Virgo Supercluster, bringing us closer to answers. Yet, even as we make progress, new questions will undoubtedly arise. That's the nature of exploration. It's a never-ending journey of discovery. So, what does all this mean for us? It means that the universe is still full of wonders waiting to be uncovered. It means that every mystery we solve opens the door to even greater ones. And it means that our quest for knowledge is far from over. If you've enjoyed this deep dive into the mysteries of the Virgo Supercluster, don't forget to like this video and share it with fellow space enthusiasts. Let's keep the conversation going. What do you think is the most intriguing phenomenon we've discussed? Drop your thoughts in the comments below. And if you're hungry for more cosmic mysteries, hit that subscribe button and ring the notification bell so you never miss an update. Thank you for joining me on this journey through the wonders of the universe. Until next time, keep looking up because the cosmos is full of surprises, and the next big discovery could be just around the corner.